All right, this video we're going to introduce the ideas of single replacement reactions and how we use the activity series to predict whether a single replacement reaction can even happen. We've been through up to this point maybe various types of reactions of the 5 that we'll study, and today to talk about single replacement reactions for the first time. So a single replacement reaction is basically this: you've got an element and you've got a compound, and the idea being that the element that's off on its own at the beginning of the reaction will try to replace an element from the compound and sort of take its place in that compound. The important thing to keep in mind with single replacement reactions is that elements only replace elements that they resemble. So a metal will replace another metal from a compound. A nonmetal will replace another nonmetal from a compound. So like iron, a metal would only be able to replace other metals like copper or something like that. A nonmetal like fluorine could replace another nonmetal like say sulfur or chlorine, but metals wouldn't replace nonmetals. And the reason, as you look at some of the example equations, it becomes clear. Metals couldn't replace nonmetals and vice versa because the compounds that you'd end up with then just wouldn't make sense, and they wouldn't want to stay together because of how their charges are used to make the compounds sort of attract to each other. So as we look at single replacement reactions, keep in mind metals will only replace metals, nonmetals replace other nonmetals, and it's important to remember that hydrogen, even though it's officially a nonmetal, tends to act as a metal. And the reason for that is that hydrogen, more often than not, has a positive charge or oxidation number in the compound. And when it does, it resembles metals, which always have positive oxidation numbers or charges in compounds. Nonmetals, on the other hand, tend to have negative charges, but hydrogen rarely does. So as an example equation for single replacement, we have this E plus Fg yields Eg plus F. It's important to note here the color combinations that I've used for this. Metals are in blue, nonmetals are in red. The metals will replace other metals. In other words, E in this case, which is off by itself, will try to come in and kick F out of the compound that it's in. So Fg is a compound, a metal with a nonmetal. It could perhaps be a metal with one of the ions from our polyatomic ions list. But in any case, the metal E is trying to replace the other metal F. And we use the analogy of this being sort of like at a dance. If a couple is dancing and another person comes over on their own and asks to cut in at the dance. We don't see this as much at dances these days because people don't tend to dance as couples anymore. They just get in big crowds and ram into each other, which isn't really dancing at all, but that's a different day. In any case, a single replacement reactions, a man might, at an old-fashioned dance or a more formal dance, a man might come over and ask another man if he can cut in and dance with the woman that he was dancing with and kick that man out, so to speak. Hopefully it's not done in a way to kick someone out, but that's kind of how this looks. So Fg is a couple, it's dancing along just fine. Along comes element E and sort of bumps F out of the reaction, and F is replaced or displaced from its compound. And we end up with, over here on the right side of the equation then, a compound, EG, where E has taken the place of F, and now F is off by itself. That was a metal replacing another metal. We can see the same thing with a nonmetal replacing another nonmetal. So here's another equation. We've got our same pair here, Fg, but here along comes element H. Now H is a nonmetal, it's in red, so it's going to try to come in and replace this element G and take its position in the pair, in the compound. And according to this equation, that's what happened. H came in and bumped G out, and now F is with H, and G is off by itself. So keep in mind here, the same compound, Fg, in our examples, has been sort of attacked by a metal, which kicked the metal F out. And then in the second equation, the compound was attacked, if you will, by a nonmetal H, which kicked the other nonmetal G out. Keep in mind that we have to watch for that along the way as we study single replacement reactions. Metals replace metals, nonmetals replace nonmetals. Here's the deal. It doesn't always work. So not every metal can replace every other metal, and not every nonmetal can replace every other nonmetal. Frankly, it would be sheer chaos if that happened. It would be anarchy. Everything would just be replacing everything constantly, and there'd be no compounds that would last. We use an activity series to tell us which elements are possibly going to replace other elements and which ones cannot. So this gives us a ranking system of sorts to tell us who can replace whom. As we look at an activity series, if you're ranked above another element on that list, then you can replace that element. But if you're ranked below the other element on that list, then you can't. So it's sort of a ranking system where the element at the top of the list can replace everybody below him or her, it, and an element in the middle of the series can replace only those elements below it and not the ones above it. So let's look at an example. This is a copy of the activity series that we handed out in class. If you didn't get one, I'll post it here along with the video. if it's on Google Classroom, or check with your teacher if you're watching this somewhere else and you don't have an activity series. You'll need one to kind of refer to. There'll be one posted here later in the video that you can look at as well. But what this is a list of the metals, some of the metals, and some of the non-metals in order of their activity. In other words, the elements near the top, like say lithium in this example, since it's the top ranked metal of all, it can replace all these metals below it from their compounds if it's given the chance. Very active, it's very sort of aggressive. There's nothing that lithium doesn't replace. On the other hand, if we consider an element like aluminum, that's somewhere near the middle of the activity series, it can replace all the elements below it on the list, but it would be unable to replace those metals ranked above it on the list. And there's never any ties. So it's not a tie situation or where one element can replace the other, and it can happen in reverse. Aluminum, for example, here could replace, say, zinc because it's below it, but zinc could not turn around and replace aluminum because aluminum is ranked higher. So keep that in mind. And it works the same way on the non-metal side. Fluorine could replace everybody below it. And phosphorus, according to this list, phosphorus could replace none of the other non-metals ranked above it since it's dead last. Now we're going to look at some examples of the sheet that hopefully you got from class. If you don't have a copy of this yet, you can copy these down into your notes, follow along right with us, and then check your work with us or questions as you get back to class. But in any case, we'll go through a few examples on here to show you some of the different scenarios. So in this first example, we've got lithium and aluminum chloride. Now, if you can recognize right away what's trying to happen here, what potentially could happen here, then you can go ahead and consider it based on the activity series from the very beginning. However, if you don't, then you recognize what's going to happen, then you might want to write the formulas out. And in fact, we're eventually going to want you to write the equations, so you may as well start with that. So we have lithium, and we have aluminum chloride. So use your periodic table, use your ions list, whatever you need, and make sure that you've got these formulas correct. Aluminum chloride, like so, okay? And it's trying to see now, does this reaction actually occur? So the question of whether this reaction can actually happen means that we need to look at it and say, who's trying to replace whom? Lithium is a metal, aluminum is a metal. So lithium is trying to replace aluminum from this compound that it's in with chloride. Question is, can lithium replace aluminum? To answer that, we have to look at our activity series here. And by looking at it, we can see where lithium is located. It's here at the top of our activity series. And we can see where aluminum is located quite a bit further down the activity series. And then we have to again evaluate, can lithium replace aluminum from this compound? Yes, because lithium is ranked above it on the list here on the activity series, lithium can sort of come in here and replace aluminum from its position since it's ranked above it. So lithium will, in fact, replace aluminum and kick aluminum out of its compound. So we're going to be left with aluminum off by itself. And you can write in the names right away, or you can do them, sorry, I just misspelled that. You can do them right away, or you can finish the formulas up first, doesn't matter. So aluminum will come out as aluminum, the metal. And then the other compound, or the other partner here as a product, will be what's left when lithium takes its place. So lithium now will come in and join chloride. Now be really careful with these. You want to consider, you don't just bring along this ClO2 and the subscript of a 3 outside of the parentheses, because in fact that was there. That 3 was there only because aluminum in this compound had a +3 charge, and chloride's -1 charge means it takes 3 chlorides to make that compound work. And so on this side, you don't bring along the 3, you just bring along the chloride and its -1 charge, and you bring lithium with its +1 charge. And then we know that lithium chloride +1 -1, that's going to work just like as it is. All right. So you don't need to show those oxidation numbers, but you definitely want to consider them as you're writing the equations. And then the compound's name over here will be lithium chloride. And we don't need a Roman numeral or anything in this case because lithium's oxidation number. Here's our equation. Now it's not balanced. I'm not going to balance equations on here because that's something that isn't the focus of this video. And it's something that I think you guys can handle. But be aware that you should balance all equations that you write. Why? Well, because equations aren't all that useful in most cases until they've been balanced. And then 2, if you actually balance the equation, if you can't balance it, you'll find out that sometimes that means you've made a mistake in a formula somewhere, and balancing it might be just a way for you to know if you've made a mistake. It won't catch all your mistakes, but it'll definitely catch a few. So let's go on and look at another example. Number 22 says manganese and iron 2 bromide. Again, I'm going to go ahead and write the formulas up for these. So manganese plus iron 2 bromide. Looks like that. Manganese is trying to replace iron. Can that happen? Well, let's look at our activity series and see what it says. Manganese is here on my activity series. Iron is down a ways. So yes, manganese can replace iron because it ranks above it. Iron couldn't replace manganese, but that's not what we have here. So yes, manganese will come and kick iron out. So I get an iron by itself. And manganese will take its place in the compound with the bromide. Now here's the question that often comes up. What about this 2? Well, remember that Roman numeral 2 in that case means that iron has a +2 oxidation number. And so in a compound, iron's charge was in fact +2. 2 plus 1 minus. But when iron is kicked out, it's no longer in a compound. In fact, its oxidation number now can be treated as 0. And by that same measure, then manganese starts out with an oxidation number of 0. And by the end, it's in a compound. So the second question then is, well, what's manganese's oxidation number now that it's in a compound? And to answer that question, we need to look at the periodic table and see, well, what's manganese's oxidation number typically been when it is in compounds? Here's manganese on our periodic table. And we see here that manganese can be 7, 6, 4, 2, or 3. That's a whole bunch of choices. That doesn't seem to help me. I don't know which one to choose. In fact, you could say manganese has taken on any one of these charges. You could pick any one you want and write a formula and balance the equation, and technically you'd be right. So you really can't go wrong with any of these choices. But which one to choose? Like, which one do you want us to choose? This is a question students will ask me. Well, I'm going to say, go ahead and choose the one that's bold, just so that we're all on the same page. The one that's bold-faced is probably the most common or most stable of the oxidation numbers. It's probably the one we'd find the most often in compounds, although certainly not the only one because of all these other ones that are listed. So go ahead and choose. If you have to choose one, pick the bold one. If you feel crazy and like, I don't want to pick the bold one all the time, fine, choose something else. As long as it's from the list, I really can't say you're truly wrong. But I'm going to go with manganese 2 here. Oops, manganese +2. Bromide still a -1. So when I put those together in a compound, I need 2 bromides, just like I needed 2 on the other side. And if I name this, now that I've chosen manganese as 2, I definitely need to say that in the name, manganese 2 bromide. Without that Roman numeral, your answer would be wrong because manganese definitely needs a Roman numeral when it's in a compound. Now, what about number 23? Copper plus nickel, 2. Well, copper's trying to replace nickel. So let's look at our activity series and see, can copper replace nickel? Now, they're a little further down the list to the bottom here, at least copper is. That might tell us the answer. Copper's way down here. And nickel's further up the list. So copper cannot come up and replace nickel. Nope, copper's ranked below. In fact, copper's quite low on the list. So copper can't replace nickel. In other words, this reaction isn't possible. And those for students tend to be the ones they like because they don't have to write the equation out. They just say, nope, not going to happen, no reaction. And go ahead and fill those blanks in and say so because that can't happen. It can't occur. Because copper is ranked below nickel on the activity series, it cannot replace it. That cannot happen. Let's look at 24. Number 24 has chlorine and potassium iodide. Now I'm going to go ahead and write the formulas again for this one because it's important to remind people here, if we haven't seen them much, or even if you have, that chlorine is one of the diatomic elements, right? Don't forget we have 7 elements that always come in pairs, and chlorine is one of them. Potassium iodide K plus 1, iodide minus 1, so that's just Ki. Now, in this case, chlorine and potassium iodide, who's trying to replace whom? Well, chlorine's a nonmetal. Remember, above the staircase line, we have chlorine, iodine, oxygen, and the rest. And sure enough, chlorine's a nonmetal. It's trying to come in here and replace not potassium, but iodine, because they're both nonmetals. That's the position chlorine wants to take in the dance here, in the partnership. And so chlorine's trying to kick iodine out. Can that happen? Well, let's look at the activity series. According to my activity series, yep, chlorine is ranked near the top. Iodine's ranked a little further down. This is a much shorter list because there aren't as many nonmetals on the periodic table. But yes, chlorine can come down and kick out iodine. So that's a reaction that can occur. So in our equation, chlorine is going to kick out iodine. And so we get iodine. Again, that's a diatomic element, so now it comes out in 2s. And chlorine takes the place of iodine in the compound. So it's potassium, not with iodine anymore, but with chlorine, or as we call it in the compound, chloride. So +1, -1, we're all set to go. Now, if you look at this and say, what the heck, I got I2 here, I only had I1 over here. Remember, we haven't balanced this equation. So when the iodines come out, what will happen is chlorine, as a paired or diatomic element, will find 2 KIs, essentially, and kick out the I's from 2 of them. And those I's then will get together, sort of share each other's grief as having been kicked out of their compound. And you'll end up with 2 KCl's as a result. So when you balance the equation, some of those oddities or those imbalances that you see will get fixed. As far as the names go, iodine, the element, is now iodine. Remember, the IDE ending that we see so much of in compounds means it's in a compound, and it's almost always there to represent a non-metal, plain old non-metal in a compound. That iodine is no longer in a compound, so it changes its name back to its original element, iodine. And then now that it's in a compound, we have to give chloride the ending that says so, and that means potassium chloride as our other product of this reaction. So you've seen in these examples now, one where a metal replaced the other in the first example, easy peasy. The second one is there to help us remember how to handle oxidation numbers in Roman numerals. So an element like iron lost its oxidation number because as it comes out of the compound, it no longer has a charge of +2. But manganese took one on because it's now in a compound and needs a charge. And manganese we chose in this case, the bold-faced charge on manganese from our periodic table. 23, we got an example of a reaction that can't happen because, again, copper was ranked below nickel on the periodic table and therefore cannot come and knock it out of its compounds. So copper couldn't replace nickel, but if it had the chance, nickel could, in fact, replace copper. And then on the fourth example we did, we had nonmetals. So chlorine trying to replace iodine was a nonmetal kicking a nonmetal out of its compound. And in this case, it was successful because chlorine ranks pretty high on our activity series for the nonmetals and could come down and knock iodine out. So you've got some examples there, one of each of the different kind of scenarios to sort of consider. The other ones that are listed here pretty much follow those same rules. What you encourage you to do is start with the formulas as we did on the ones that actually worked out. Start with the formulas and look at the elements that are involved and make sure you're considering which elements are replacing which other elements from the compounds because they can be a little easier to see if you're looking at them as formulas. I'll also mention that I'm going to sign off that number 29 on this list is the only one that's at all tricky. The rest of them are very straightforward and follow along with the ideas that you've seen in these 4 examples. So work on the rest of the page for the next time we see you in class. And if you have questions before then and you can catch us, do. If not, bring those questions to class and we'll take care of you then. Thanks.